So I want to unpack a pneumatic language for you that's really very powerful. It's awesome. It's very much like ladder logic, actually, in that it's, you know, a kind of a logical decision of things, or a logical programming language. It's also a wiring diagram in this case. Sequential statements are also a hosing diagram, and they're a logical programming language as well. Pretty cool. So what we can do is we can take some description of an operation and we can turn it into what we call a control statement. And then from there we can take the control statement and turn it into a sequential statement. And then from there we can actually just build a circuit from it. Pretty cool. So let's jump into what we're talking about here. What I really want to highlight is the fact that cylinders can be required to actuate or move in a pre-programmed sequence. Sometimes it's pretty complicated, but for now we're just going to start with pretty kind of basic kind of movements. Okay, pneumatic and hydraulic internal sequential control is a type of control that uses limit valves and relay valves. Yeah, pretty cool. So, and with those, we can add logical decisions without any electricity, which is so cool. Yeah, we can use relays that are pneumatic relays, just kind of like how we use relays that are electrical to add more logic. Sequencing by position sensing. Yeah, pretty cool. So essentially, sequencing of a pneumatic system is the aspect of the control of the sequence of events within respect to the actions of the actuators in the system. What? Well, simply put, it's when they move and how they move within respect to each other. So with any sequence of events, there must be a reasoning or logic behind when something happens and why it happens, and more specifically, what signals create that control. Well, the signals come from the position sensing. How do we sense that something has a particular position? The limit valve. We can also do it with a limit switch. But what I'm doing is I'm sticking to pure pneumatic control. Pretty cool. And we can do that with limit valves. So a limit valve is going to tell us that a cylinder has extended, or fully retracted. Okay, so here is the development of a control statement. I don't want to get into sequential statements just yet. We're going to take a look at the development of just a simple thing called a control statement. It's actually really basic. And then from there, we're going to look at how we can take that control statement and turn it into a sequential statement. Okay, here's an example. A cheese press uses pneumatic actuators to hold and press onto a block of cheese. Okay, the holding cylinder extends to clamp onto the cheese, and then a press cylinder comes down and presses the cheese, and then that press cylinder retracts, and then the clamp retracts. Pretty simple. So what I've just talked about is the actions of two cylinders. Starting with the operational parameters of the system, the control statement is established. Okay, so what we do is we take these operational parameters and we establish a control statement. So we have to kind of name the actions. More specifically, we name the cylinders associated with those actions, and we name them with an uppercase letter that is associated with whatever it is that they're doing. Okay, in the cheese press application, we will call the clamping cylinder C and the press cylinder P. I think that makes sense, and we can wrap our heads around it. And we have to do that because when it gets really complicated, you may have 5 or 6 or 7 actuators, and you call each actuator a different name because you're naming the actuator for what it does. So you probably want to use an uppercase letter to establish kind of the name of that's associated with what it's actually doing. I think that makes sense. So let's move forward. From the operational parameters, we develop a control statement, naming each cylinder with a letter and listing them in progression. And then we use a plus and a negative to indicate the action, in that if it's extending or it's retracting. So I'm just going to write this down in a list, nice and simple. The clamping extends, the clamp cylinder extends, C+. Then, from the operational parameters, the next thing that happens is the press come down. Okay, so the press cylinder extends, and then the press cylinder retracts, and then the clamping cylinder retracts. So P minus C minus. So then we write them all down into a control statement. Yeah, pretty simple. So that is my control statement. C plus, P minus, C minus. From there, we can build a sequential statement. So let's look at another example and start from scratch. A little bit more complicated, a little bit more wordy. And it's important that we actually learn how to take these words and turn them into control statements. How to develop a sequential statement. We're going to take our functional parameters, we're going to turn it into a control statement, and then from there we'll talk about what a sequential statement looks like. These parameters look like this. In a glue station, there's an assembly process at a glue station. There are actually 4 cylinders here. I'm sorry, there are 2 cylinders and 4 actions, as we will see. But we've been given these instructions, maybe by somebody who's already got an engineering mindset. But sometimes you may just get really instructions from somebody because they're not a critical thinker as far as engineering goes, and they may not know exactly what you need to know. Sometimes you have to kind of extrapolate a control statement from what the description is. And sometimes maybe at that time, you may say, oh, there's a gap here. It doesn't say when this retracts. Yeah, and that control statement, it will show you that there's something missing. So you can go back to the person wanting you to develop this, and you can say, hey, when should this retract? And they may say, oh yeah, that's right, I didn't think about that. Or maybe they didn't know that they had to tell you. Moving forward, here's a nice, simple step-by-step example. Placement cylinder extends and places the glue applicator into the glue. Okay, whatever that means. You can picture it as you go. Let's just move forward. An application cylinder retracts and sucks up the glue into the applicator. Okay, so it seems as though there's something that extends and it has something on it. Okay, and that something is the glue applicator. So this thing extends, the glue applicator is on it, and then the glue applicator actually sucks up, so it retracts and sucks up. And then the placement cylinder, this arm with this applicator on it, retracts, and then the glue or the application cylinder extends. So let me just draw a picture of that. Okay, here we go. Now the control statement's on the top. I think it'll make sense. I'm going to back up a slide. But I'm just going to say it's nice sometimes to draw a picture of what's going on. If you can't wrap your head around the operational parameters, or the discussion of what it is that is happening, just draw a picture. Okay, so I'm going to go back. I'm going to say this again. We're just like we did in the last example. We're going to write these things down, and then we're going to write the action beside. Okay, placement cylinder extends. It said that in the description. Okay, P plus. It's a placement cylinder. And then the application of cylinder retracts. Because it did say that there. It says the application cylinder retracts. Okay, sucks up the liquid. Okay, and then the placement cylinder retracts. Okay, and I think it said that there. The placement cylinder retracts. Oh, it's pretty simple. Okay, and then the application cylinder extends. And it looks like this. This is actually what's happening here. So we just write these things down. It's that simple. We just take this step by step by step by step, and you write it down into a control statement. Okay, so we're done, right? No. Then we can make this into a sequential statement. I need to talk to you about sequential statements. They are so cool. There are some rules to sequential statements, just like kind of like BEDMAS. If you just follow it, you can't go wrong with the math. If you follow a sequential statement, you cannot go wrong. There are just some rules and regulations that are associated with that. So the last step here is to make a sequential statement. Sequential statements are cool because not only are they logical instructions, just like a ladder logic diagram, it's a programming language, but they're also a hosing diagram. Really, we're going to show you how to do a hosing diagram in another video. Right now, I just want to focus on how to develop a sequential statement. Okay, let's take a look at this. There's some basic rules for a sequential statement. Okay, so what it does is it outlines a sequence of cylinder motions. It outlines how limit valves and cylinders interact, and it outlines where each component gets its air from. Is that important, where each component gets its air from? I mean, it looks like it all just comes from these symbols above. This is where the air is coming from. This is actually really important. Right now, we won't see that as so important, but as we get into more complicated sequential statements, you'll see how that's very important. Okay, moving forward, these are the rules. All arrows pointing down supply air to limit valves. Okay, so you can't have an arrow pointing down unless it's supplying air to a limit valve. It doesn't supply air to any actions. It doesn't supply air to anything. It just supplies air to limit valves, which makes me kind of think, how do I define a limit valve? Well, the limit valves are the lowercase letter of the action. Because if we take a look at it, if we take a cylinder, the cylinder can have an outside limit valve, A+, and an inside limit valve, A-. We indicate the limit valves with lowercase letters. So what we're going to do is we're going to take the exact same control statement right here, exact same control statement, and we're going to rewrite the control statement with limit valves. Before we do any of these arrows or anything, we just write it down. So we're going to say P+ and lowercase p+. Uppercase A-, lowercase A-, colon, uppercase, lowercase. And then from there, we can follow these rules. So essentially, right now, we can just see in this sequential statement that every single limit valve gets air directly from supply. That's what that symbol is for. It indicates that air is coming directly from supply, right from the regulator, the pressure regulator. Okay, good. So all arrows pointing up control cylinder actions. Okay, so what's going on here? Every arrow that points up is controlling a cylinder action. Cylinder action is either an extension or retraction. Okay, so that's it. So every single arrow that points up is controlling a cylinder action. No arrows point up do anything other than control cylinder actions. Okay, good. So all limit valves have air supplies coming from above. Okay, all limit valves have air output exhausting from below, or exiting from below, pardon me. So take a look at this. Has air coming into it, a limit valve passes air through it, it comes out, and then it goes to an action. But if we take a look at any one of these limit valves, we can see there's an arrow going into the top and a line coming out. Every single one. So if you're developing a sequential statement and you don't have an arrow coming out or a line coming out of a limit valve, something's not quite right. All cylinder actions have arrows denoting cylinder control. All cylinder actions have arrows denoting cylinder control. So as you're going through your sequential statement, if any one of these actions does not have an arrow going up to it, there's something missing. Okay, so I want to add an element of maybe one more bit of complication, and it doesn't actually get much more complicated than this. I'm going to add brackets. Yeah, pretty cool. So brackets indicate that two actions are happening at the same time. Actually, we can have three actions happening at the same time if we had 3 cylinders, or maybe if we had 4 cylinders, or if we had 5 or 6 cylinders, we could have 3 or 2 or 4 or however many. If they are inside a bracket, they start to happen at the same time. Each action in brackets is triggered at the same time, which doesn't indicate that they get to their final extension or their final retraction. They don't complete their stroke at the same time. At least it's not guaranteed that they do. But if they're in brackets, it's guaranteed that they will start to extend at the same time. It's important that I mention that because some cylinders actually move faster than others, and some have further to go. Some are pushing loads, some aren't pushing loads. So for some reason, they may move more quickly or more slowly than another cylinder. But if they're in the same brackets, they start extending or start retracting at the same time, or more specifically, they start their action at the same time. Their action arrows come from the previous valve and is shared between all actions in the brackets. Okay, what does that mean? Well, it's right here. Take a look at this. These two arrows go up to the same thing because they start happening at the same time. They get their impulse or their signal at the same time, and they get it from the limit valve previous to the bracket actions. And we can see that from here. What's going on is this air comes from this limit valve and then it makes this happen. So essentially, when cylinder B is retracted, after that's done, these two will start to do their action. And they will do that because these two actions get air directly from this limit valve at the same time. Valve supply in brackets. Now, this is a little bit tricky. This has to do with an and it also has to do with the speed of the cylinders. You will see this in many examples in the labs. What I'm saying here is that I'm going to say that C moves much more quickly than D. So C extends really quickly and D retracts very slowly. Or maybe we could say that C extends very quickly and D retracts very slowly. With that, did I just say that backwards? Yeah, whatever. Just flip the logic, okay? So what I'm saying is that they're not going to get extended or retracted at the same time, but they're going to start at the same time. What we need to do is we need to put an and through them. And the reason for that is because at the end of them both finishing their job, then something else has to happen. Whatever is after that is going to take place. If I were to only take air from the D, if I were to just put this air directly here to the D and go this way, then if D got there really quickly, if D retracted really quickly, it wouldn't give time for C to fully extend. So what I'm saying is here, we have to put them in an AND configuration. So we can say that C has fully extended, okay, and then C plus, the limit valve C plus, becomes passing. It becomes open. Air comes out of it, and then it supplies limit D minus. When it is active, it becomes passing. Air goes through it, and then the signal can say, okay, we're done. These two actions are done happening, go on. So unless both of them are done acting, the next step shouldn't happen. So we put the air through them like this in an AND configuration. So air to A plus will not happen unless C has extended and D has fully retracted. Okay, good. So this ensures that the signal leaving the last valve, in this case D minus, will not actuate the next until all of the actions have happened in that bracket. Okay, good. So now we've established some basic rules here, and we can just see that this is really simple, and this is kind of like highlighting the whole thing here, and we can see that that's extension, extension, retraction, retraction. And if we were to give a signal to this action, that signal can just disappear. It can be momentary. Watch this. This is really cool. If I gave a momentary signal to A plus and said, okay, just go, it would go. And then even if that signal disappeared, A plus would still continue to extend as long as I'm using a double pilot DCV. It would extend, and then when it extends, A plus would become passing. It would tell B plus to actuate and move. When B plus actuates, this becomes passing, and it tells A to retract. And then when A retracts, it's going to then have air passing here, and it's going to tell B to retract. Once B retracts, well, it'll just stop, unless I can turn this off somehow. I can stop this line. Essentially, as soon as I just hose this up, it would just keep going. Boom, do, 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 forever and ever and ever. But maybe there's something I can put in here to add in here, and I think maybe we'll have to put a push button in here in a bit, but hold on. What I just want to say is that this can go on and on and on. In this case, it's 3 cylinders. It can go on and on and on. Now, it could get more complicated because we may want to put brackets in. This is a much more complicated one with brackets. It's got 3 cylinders, so there are 6 actions altogether. And actually, we can boil that down to kind of 5 because one of them happens at the same time, but we won't get into the logistics or the terminology of all of this just yet. Let's just kind of unpack this sequential statement with a bracket with 2 cylinders in it. Okay, so now, the first thing that's going to happen here is that A plus and B plus start to extend at the same time. Now, we're just going to assume that B plus is really fast, okay? If I were to not have this air supply here, and if I were to not have this, and I just got rid of it, because they're going at the same time, and I only put air into B plus, if B plus was really quick, and A was slow, B plus would get out and the air from here would go into here and it would make this happen. But you know what? A hadn't fully extended all the way. We don't want that to happen. We want this to complete its cycle and then it can move on. And you know what? You can manipulate this as many different ways as you want. You can put the bracket in the middle. You can put the brackets around B plus and C minus, or even B plus, C minus, and A plus if you wanted, and move the brackets around. As long as you follow the rules, you will not get wrong. So let's just follow this. Right here, I've got air coming here and ending through these 2 limit valves. Air that goes into these is coming from the action that's previous to it. Yes, and by the way, this wraps around and around and around and around. So we can kind of say that the action after C plus is A plus, B plus. That's the action. The actions, A plus, B plus, happens after C plus. Okay, good. So just as though B minus happens after A minus, it's a wraparound concept here. So the first thing that happens is that there's one all the way on the left. These guys start to extend at the same time. Once they're fully extended, both of them, then air comes out of here and it makes this extend, and once that extends, and blah, 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 on and on and on and on. I could put many more cylinders in here. If I wanted to put the bracket in between B plus and C minus, I could do that. As long as I follow the convention, it's going to work. I need you to just go ahead and practice some of these. There are many of them posted on the blackboard. Practice them, and just once you get them, bang, 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 over and over and over again, you can't get them wrong. This is a basic sequential statement. We actually call this a sequential statement without conflict. There are sequential statements that do much more complicated processes. There are sequential statements with conflict resolution, with something called a cascade method, whatever that means. We won't even get into that. It's way beyond the scope of this course, and we don't need to do that. But I need you to understand how to design a control statement from the description of a process. And then I need you to take the control statement and turn it into a sequential statement. And that's it I need you to do for this video. There's another video on how to actually take a sequential statement and turn it into a hosing diagram and hook it up actually to a circuit and make it go. We'll talk about that later. For now, you just need to practice these. That's it. Goodbye.